Good morning, everyone. So the number one most requested thing for me to go over is how to add two and more than two non-perpendicular vectors. So let's just look here at the original video. If you want to go watch the original video, all of the videos that are posted on Classroom have a section title and a title, like a little title telling you what the information is. So you should look for the one that says something about adding non-perpendicular vectors or 2 plus non-perpendicular vectors, something like that, if you want to rewatch that video. Okay, so when we're adding, let's just look at this example that we already looked at. So we have a plane that's flying northeast and then east. So this is two-dimensional, right? Because one-dimensional, 1D, is up and down, right and left, or north and south, east and west. There's no diagonal in north or in one-dimensional. But with two-dimensional, we have diagonals. So remember here we have a plane that's flying northeast. This is our A vector here, and then directly east. So how do we find our resultant? So remember it's going to look something like this. We have northeast and then directly east. And we're supposed to find I'm going to make this pen thicker. A little thicker. There you go. Find our resultant here. And remember, very not straight line, sorry. Remember, we are going to break up this vector into its vector components. So we have an AX component, AX, and we have an AY component. So I'm going to also kill two birds with one stone here. So someone asked me also really quick that, like, how do I know to draw them like I just did? How do I know to draw it this way and this way instead of drawing it this way for AX, or for AY, sorry, and this way for AX? How do I know which way to do that? Or how do I know which one to do? Well, in this case, it doesn't actually matter, because you see here we have this AX pointing to the east, and we have this AX pointing to the east. Here we have the AY pointing north, and here we have the AY pointing north. So as long as you read what the text is telling you, or read the direction, which direction it's going. So if it's going northeast, as simply as I just told you like this, you can very easily tell that you're doing this correctly by putting the vectors, one is going east and one is going north, and the vector, the resultant of that is going to be northeast. So really just thought of that right now, because some of you, actually two of you, asked that question. All right, so remember that our A resultant here, or our A vector, our northeast vector, has a horizontal component and a vertical component. So anytime we see non-perpendicular line or non-perpendicular vectors like this with this, resulting in non-perpendicular, then we have to fix this nasty vector, this angled vector. And the way that we can fix that is by putting it into its horizontal and vertical components. All right. So we solve for the horizontal and the vertical components, and then we add them all together. So I take this AX and I add all of the horizontals together, so AX and B, and then I put the Y on there. All right. So that's a very basic way of doing that. Let's look at an actual example. So here we have a plane flying 45 degrees in the counterclockwise of east direction for 260 kilometers. Then it changes direction and flies exactly due east for 130 kilometers. So I've drawn that here. So I basically just given our previous problem, I've given it values. So remember what we did is, we didn't know this part yet. What we did here is I need to put this vector here, I need to break it down into its vector components, into its ax, into its ay. And then, once I do that, I can add those to b in order to solve for my resultant. So what I did is I used the trigonometric method in order to solve here for my a vector. I solved for the ax component and the ay component. And if you want to see me solve that, you can go back and watch that yourself. I used the Pythagorean theorem first, and then, or no. No. Sorry. Scratch that. I used the trigonometric method in order to solve for this. And then once I knew these two, I had 184 here, 184 kilometers and 184 kilometers. What I did then is I added those here, down here, to B, right? So I made, and I added my horizontals, so my AX component plus my B component to make one big, long horizontal vector component. And then I did my AY on top of that. And then I could use Pythagorean's method to solve for R here, and then I could use the trigonometric method in order to solve for the internal angle and therefore the outer angle to figure out the counterclockwise of east convention. So if we have more than, let's do an example, actually do one. Okay, I just made up a new example. Okay, so we have a runner and she's making the following motions during her 5K run. She's going to do 0.72 kilometers in the 45 counterclockwise of each direction, then 2.8 in the 100 counterclockwise of each direction, 1.10 exactly north, 0.9 kilometers in the 63 counterclockwise of each direction. So what we're going to do is we're going to draw this all out first, and then we're going to work our way from there. So we have a 0.72 kilometers in the exactly 45 degrees counterclockwise of east. So this is 0.72. All right, then from there, I'm going to change colors here and go to green. So we're going to call this A, B, blue, C, and we'll do purple for D. All right. So that's A. Now we'll do B. B, we're going to go in the 100 degrees counterclockwise of east direction, which this is 90, so we're just a little bit to the left here. Yeah, and we're going to do that, but that's going to be for quite a bit ways longer, so we're going to make that a longer vector here. Scoot this guy down. I'm going to scoot this whole thing down. Yeah. All right, so we have, so we have whatever it was, 2 point something. That might be a little too angled. We'll do like this, more like that. We have 2.18 kilometers, 2.18. Then we're going to go 1.1 kilometers in the exactly north direction. Make this guy smaller. Okay, we're in blue. So we're going to go exactly north for 1.0. Then we're going to go an additional 0.9 kilometers in the 63 degree counterclockwise of east direction, which would be something kind of like that. This is going to be 0.90. Okay, so wow, we have something that looks a little crazy. So we're going to start here, and our resultant is going to go all the way up to here, right? This is R. But what we are going to do is we have to resolve these into the first step is going to be to turn all of our angled vectors, which we have 3 here, right? We have A, B, and D are not in either perfectly horizontal or perfectly vertical. The only one that is the one that's going exactly north, which is C. So we have to resolve these other 3 vectors into their vector components before we can do anything. So let's start with A. So for A here, A is in red. We have, oh no, what happened? There we go. We have a vector that looks something like this, and it's 0.72 kilometers. We know that we are going in a 45 degree direction. So this angle here, this right here, is 45 degrees. How do I know that it's that angle that I'm talking about and not this angle? Well, I'm not talking about the way that you can know where to which angle you're talking about is think about the start of that vector. So the start of this vector is down here, right, at the vector's tail, right? So the point that is the vector's tail is going to be the angle that we're talking about. I can't put the angle up here, 45 degree angle up here, because this is the vector's head. I can only put my angle near the vector's tail, which is right here. That was another question, so I think I've answered like 3 questions now. Okay, so first what we're going to do, I'm going to label this AX and AY. And then what we're going to do is we're going to solve for AX and AY. Remember, we have to use the trigonometric method. First, what I'm going to do is I'm going to do sine of theta, which in this case is actually 45. The sine of 45 is equal to the opposite over the hypotenuse, which is AY over 0.72. So with a little algebra, I can rearrange this to get sine of 45 times 0.72. I did that by multiplying both sides by 0.72, and this is going to equal AY. When I plug that in, 0.5 and 2 significant figures, 5.1 kilometers equals AY. All right, so this equals 0.51 kilometers. And AX, now we will solve for AX is going to equal, let's see. So I used sine to solve for AY, so I'm going to have to use cosine of 45 to solve for my horizontal component. So cosine of 45 is equal to adjacent, which in this case is AX, over hypotenuse, which is 0.72. And when I rearrange, I get something very similar. Cosine 45 times 0.72 equals AX. And I get 0.51 kilometers equals AX. All right, that makes sense. 0.51 kilometers. Okay, so now I have my first horizontal and my first vertical components here. So now what I'm going to need to do is resolve B into its horizontal and vertical components. Before we move on to resolving the green one, B here, someone else asked a question, and I helped Yusra with this before, so I hope maybe Yusra can help as well if you're struggling with this. Some people have been saying that when they put their these values, when they plug these values into their calculator, they're doing the exact same thing as me, but they're getting the wrong answer. And the reason for that, or getting a different answer, the reason for that is because your calculator is in radians rather than degrees. So to fix that problem, you're going to get your calculator out right now and fix it right now. So I think for every TI calculator, it should be the same. If this isn't the same, then what you're going to Google is how to switch calculator from radians to degrees, and you put in the type of calculator you're using. For example, I'm using a TI-84 calculator, right? So I would say, how to switch from radians to degrees on TI-84, and it will tell you how to do that. But I'll tell you right now, I'll be Google for you right now. So what you're going to do is you're going to go to mode, which is right next, it's in the upper left, next to second. You're going to go to mode, and then that should be the third one down. You're going to see it says radian and degree, and you want it to be on degrees, not radians. So switch it if it's on radians, and then just do second and quit. And that should fix the problem. If you're still having issues, then you can WhatsApp or Google Classroom me. All right. So Google Classroom comment me. To me, Google Classroom comment me. You know what I mean. Tell me that you need help if you still need help. Or use Google that would work too. Okay, so now we're going to look at B, which looks something like this. And this is 2.18. All right, so this is another way of thinking about this or looking at this is like trying to figure out which way we should draw our vectors here, because someone was saying, how do I know if I draw the vectors like this and like this, or like this and like this? Well, if I draw them this way, my vector would be going in the opposite direction, right? Look at where I would start to draw the resultant. I would start here, and I would end here. That is not right? The vector would be pointing in the southwest direction instead of the northwest direction. So one way you can think about this is, what way is the vector pointing? Well, it's pointing kind of northwest, so I should have a west vector and a north vector. All right, it's not pointing southeast, so I don't need an east and a south. I need a west and a north. So that's another way to think of it if I didn't help you, if you didn't understand what I was saying earlier. Okay, so here we have a west component or a BX component, and we have a vertical component, which is our BY component. Now we're going to do exactly the same thing as we did before. Oh yeah, don't forget we have to figure out our theta here first. Okay, so in this situation, I gave you the counterclockwise of east, which means from here to here, right? I told you that it was, 100 degrees counterclockwise of east. So this right here is 100 degrees counterclockwise of east. In a straight line, how many degrees do we have? We have 180 degrees, right? So we have 100 on this side. That means that here we have a theta. I'm using too thick of a pencil. Our theta and I want to erase all of this. Oh no. Okay. Our theta here, right here, is going to be 80 degrees because we're going in the 100 degree counterclockwise of east direction. So we have 80 degrees left. So inside our triangle, we have 80 degrees. Okay, now we can do sine of, I'm going to use thicker because that's hard to see, sine of 80. And that's going to be equal to opposite, which is by, over hypotenuse, which is 2.18. Rearrange and solve. And we get that by equals 2.15. All right, now we're going to solve for bx here. And we're going to do that by doing cosine. Cosine of 80 of our theta is equal to the adjacent, which is bx, over the hypotenuse, which is 2.18. And when we rearrange and solve, we find that bx is equal to we have three significant figures, so we're going to say 379 equals bx. 0.379 kilometers. Whew. Okay, so now we know A and B, and we already knew A and B, but now we've put them into their horizontal and vertical components. So we got horizontal and vertical, and we got horizontal and vertical over here. All right, so now what we need to do, well, C is already in the vertical direction because it's pointing exactly north. So we don't have to do anything with that one, right? It's perfect. It just doesn't really look that perfect here. It's supposed to be directly north, but I kind of have it to the left. Okay, but for D, we need to resolve that one into its horizontal and vertical components. So what do we have? We have 0.9 kilometers at 63. All right, so this is going to be D. D is right here, and it's at 63 degrees, so it's kind of like this, and it's going to be 0.90 kilometers. Okay, so we're going to do the exact same thing. We're looking for dx, and we're looking for dy here, right? So I think you know what we're going to have to do. We have our theta is 63 degrees, and it's inside the triangle, so we don't need to do any additional steps for that. So sine of 63 degrees is equal to the opposite, which is dy, over the hypotenuse, which is 0.90. Rearrange and solve, and we get 0.80 equals dy. So there's our 0.80 kilometers. That is our vertical component. Solve for dx in the same way that we've been doing this so far. We have our cosine of our theta, which is 63, is equal to the adjacent, which is dx, over the hypotenuse, which is 0.90. When we rearrange and solve for all of this, I find that dx equals 0.41 kilometers. Okay, so now we have all of our vertical and all of our horizontal components. So what we're going to need to do now is we're going to add up all of our vertical and all of our horizontal components, head to tail method, not head to tail method, but in the head to tail fashion. And then we're going to solve for our resultant, right? Because it doesn't matter which way we add these up in, right? Our resultant is still going to be the same. We're going to start here, we're going to end here. So let's begin that. Okay, so here I have everything I just solved for. So I have my horizontal and vertical components for A, B, and D, and then for C, it's already just perfectly vertical, so we are not going to do anything to that one. So what we're going to do is I'm just first going to take all of my horizontal components. I'm just going to, I didn't draw this properly. I forgot arrows, really? Okay, take my horizontal components, starting with AX. So we're going to take AX, and I'm going to label all of them. This is actually I'm not even going to label them. I'm just going to put the value, 0.51. All right, we got AX. Now we have B, which is in the opposite direction. So we're going to add this, but we're going to do it in the opposite direction. So we're going to go back about right there. And this is 0.379. And I'm going to put a little negative in front of that just so we remember to subtract it when we're adding these all up together. That's B, the BX component. Then we have DX, and DX is 0.41 in the positive direction. So since I have to start here, you can't see my pointer, I have to start at where I ended, right? So I go here, and I don't pick up my pen. I go backwards. Now I need to go 0.41 in this direction, 0.41. Wow. Okay, so before we move on, no, we won't resolve it yet. Let's just leave it like that. Okay, so there we go. Those are our three vectors in this situation. If this is too confusing for you and you don't like how it looks, or if you're like, what the heck? when you first start doing the addition of the horizontal components, you can look at the direction of all of them and decide, okay, well, this one is in the opposite direction, so what I'm going to do is I'm going to start with that one. If that's easier for you, you can. And if that would look like something like this. It doesn't matter. Remember, it doesn't matter the direction or the order in which we add any of these horizontal or vertical components, as long as they are head to tail and we're adding them all and putting them all in there. So if we were to start with the one that's in the opposite direction, it would look something like this. We'd start here and go back 0.379, and then we could just go ahead and go forward with our regular. This is 0.51, and again I'm going to put a negative in front of that so I remember when I'm adding them up in the next step, and then I can go again 0.41 here, whatever works for you. Or another way you can do it is you can start with the ones that are all in the same direction. So you could start with 0.51, then you can go 0.41, then you can go backwards 0.379, right? And remember to put a negative in front of that. So whatever's easiest for you to see, okay? Because what we're going to do is we're going to add up all of these values and we're going to make one nice horizontal component. So we can do that. Let's keep going with our, let's do it now. That's easier. So what I'm just going to arbitrarily choose this one. We're going to add up all of our positive vector components, which would be 0.51 plus 0.41, and then since 0.379 is in the opposite direction, we're going to subtract that. And when we do, we get a vector length in the, I don't like this color. We get a vector, a horizontal vector in the eastward direction that is 0.541 kilometers long. All right, now we can add or put together all of our vertical components. So let's do that on here. We have our AY, which is 0.51 kilometers. Then we have our BY, which is 2.515 kilometers. Then we have our blue one, our C, which is 1.10 kilometers, and finally we have our DY component, which is 0.80 kilometers. All right, now we have a resultant. If we start down here and go up here, that looks like the resultant that we drew initially, right? But without all this craziness in the middle, right? So these are the same, in the same direction, they're about the same length. So we're good to go. We just now have to add up all of these so we know the actual length rather than having 4 little pieces. We need to know the actual length of this this vector here, this vertical vector. So let's add all of those up. And we don't have to erase it, but I'm going to because I want it to look pretty. And this will be pointing all the way up like it was, but now it is 4.56 kilometers instead of that ugly 4-piece one like we had before. Okay, so we are almost done with solving for the resultant displacement of this runner. That is do you see how this could be a quiz of like 2 problems, because it involves all of these different components in just this one problem. So now to solve for R. Okay. All right, so the first thing we're going to have to do is we're going to have to use Pythagorean's theorem in order to solve for the length of R, the magnitude of R, that because we don't know any angles, right? We know a 90-degree angle, but that's not going to do anything for us right now. Okay, so solving with Pythagorean's theorem, we're going to do a squared plus b squared equals c squared. This is a squared, this is or a, b, and c. So we have 4.56 squared plus 0.541 squared, and this is going to equal r squared. When I plug that in, I get 21.1, and if I take the square root of both sides, I find that r is equal to 4.60. Alright, well now I know this is 4.60. So the magnitude of her displacement is 4.60. Now to find the direction that she's running in. To find that, this is my theta here, right? Because here's the start of my resultant vector. So that's where the angle is that I'm looking for. So to solve for that, I'm going to do sine of theta is equal to the opposite, which is 4.56 kilometers divided by the hypotenuse, which is 4.60 kilometers. And when I do that, I get that sine of theta is equal to 0.99. Well, there's three significant figures though, so it'll be 991. All right, let's take the inverse sine of both sides to get rid of that, and we find that our angle here, our theta, is equal to 82.3 degrees counterclockwise of east. All right, so that is it for that problem. And this is, you could have two problems like this on the quiz, or one problem like this and one problem like another one, because this already took us like 15 minutes, right? So be warned that you need to understand how to do this, because you're going to see a problem like this on the quiz for sure, and you might see two. Okay, so that is how we solve using two or more non-perpendicular vectors. We have to put them into their horizontal and vertical components. Every angled vector needs to be put into its horizontal and vertical components. Then, once we've got all of them in horizontal and vertical components, we can add them all up to solve for our one big long horizontal and one big long vertical. Okay? Then what we do is we solve for the magnitude and the direction of theta. Another question that someone asked me was, do we put it in, well, actually, let's just look now at some how we do some people wanted me to go over how to do counterclockwise of east convention, so we will do that. Not just counterclockwise, sorry, I'm trying to write here, not just counterclockwise of east, but all of the others. So we got to draw our compass here, or our axis, if you will. So I'm going to just northeast, southwest. Okay, so in order to know what convention we should use this in, so to do the counterclockwise of east convention, we have to look at what direction the vector is pointing, first of all. So this is pointing this way. So counterclockwise of east means you start on the east axis, right? Or on the line that's pointing east, on the x-axis, on the east side, not on the west side, on the east side. The east side? Okay. I don't even know what that's from. That's so stupid. All right, so we have this, and we're going to go counterclockwise until we hit the line. Okay, so that's the counterclockwise of east convention. This could be whatever this value is, x degrees. I don't know what this is. So that's what I mean by counterclockwise of east. Because if I just tell you we're going 100 degrees, that's the direction. Do I mean 100 degrees counterclockwise of east? Could I mean something else? Could I mean something like, what if I was actually going this way? This could be 100 degrees. How? Because if I started at west, if west was my starting point, and I go this way 100 degrees till I reach the line, right? Or if I'm traveling in a 100 degree direction away from the western axis, right? This is 100 degrees. This is 100 degrees south of west. We're going in the southern direction. We're going south from west. All right, what if, but this could also be 100 degrees. This could be 100 degrees counterclockwise of east, but it could also be 100 degrees north of east, because I'm going in the northern direction starting from east. This could also be, rather than being 100 degrees, well, let's think of another one that could be 100. So this could be 100 degrees here. This could be 100 degrees, let's use a different color, going this way, this is 100 degrees north of west, right? Because we're going in the northern direction from the starting point of west. And then also this right here in this direction could also be 100 degrees. I'm getting a little bit messy. We saw this. There we go. Okay, so we have 100 degrees there. We have, forget it. We could also have 100 degrees here is what I was saying. So this is also 100 degrees. This is 100 degrees in this direction, south of east. 100 degrees south of east. Okay? Because if we start at east, we're going to, that would be a good idea. Okay, we're going to make an arrow, and then we're going to select it. Can I do this? Okay, we're going to start at east, and then what we're going to do is we're going to not make it bigger, but can we rotate? Yes, perfect. Okay, we're going to start at east, and we're going to rotate 100 degrees in the southern direction, and now we are 100 degrees south of east, right? If I wanted to do 100 degrees in this way, if I do this way, 100 degrees. How is that 100 degrees? Well, like I said, it's 100 degrees north of west. How do I know that? Whoops, undo that. Or how do I get that wording? Well, if I'm this arrow here and I'm starting at west is my starting point. Now I'm going to go 100 degrees north of west. Well, I'm starting at west, and I'm going to rotate this 100 degrees in the northern direction. Now I am 100 degrees north of west, right? So this is why we need to really specify what we're talking about, because 100 degrees could be in 4 different directions. We don't know. Counterclockwise of east is the most common direction that we're going to see and that I'm going to ask you for, but I'm also going to trick you. And instead of saying in the problem that we just did, instead of, where was it? Here. Instead of saying in the counterclockwise of east direction, I'm going to say 63 degrees in the in north of west direction. That is not the same. If we look at 63 degrees, all right, so I said 63 degrees north of west. That would be somewhere around here. Whereas this is 63 degrees north of west, whereas 63 degrees north of, or counterclockwise of east, is here, right? So the way I got that, or not the way that I got that, but the way I can think about that is I'm starting here at west, and I'm going to go 63 degrees north of west. I'm going to, I can't see where my tail is, but I'm going to rotate 63 degrees till I'm here, right? That would be 63 degrees north of west. If I wanted 63 degrees counterclockwise of east, I'm going to start at east, and then I'm going to rotate in the counterclockwise direction for 63 degrees until I get here. All right? Okay, so I think that covers everyone's questions. Let me double check. All right, there were just a couple more questions. So some people were asking me, what does perpendicular mean? Perpendicular are lines that make a right angle. That's perpendicular. Lines that do not make a right angle would be parallel lines, right? We're not going to see any like that. Or what we are going to see are angled lines. This right here is not a right angle. This is not a 90-degree angle, right? So this is non-perpendicular, and this is perpendicular. Perpendicular means making a 90-degree angle. Someone else wanted to know, what was the wording? Oh, when we're adding one-dimensional and two-dimensional vectors. So remember, a 1D vector is something that is already vertical or already horizontal. These are 1D vectors, right? 1D means up or down, or left or right, or north, south, east, west. Right? All right. So they're all in a perfectly horizontal or perfectly vertical direction. But when we have our 2D vectors, those are angled vectors. Those are not in pretty perfect, they are not horizontal and vertical. They are angled away from horizontal and vertical. They're things like that, or that, or that, right? None of these are exactly on the perfectly horizontal and perfectly vertical axes, right? They're angled. So when we are solving for the resultant of, well, I drew these the wrong way, right? Like they would have to be, the arrowhead would have to be over here. Okay, when I'm drawing the resultant for 1D, it's pretty simple. I would be given X and Y, or A and B. It would be easier if I said A and B. I'm given A and B, and I have to solve for R and theta here, right? Okay, that's pretty straightforward. We use Pythagorean's theorem and the trigonometric method. But if I'm given an angled vector, for example, this angled vector, we're going to use this one here. What I have to do first is I have to turn it into a set of one-dimensional vectors. I have to find the vector components of this R here. But I would actually know, I would be given R, I would be given a value. So we're going to say, 5. And I would be given a value of theta here. I would know that it's 65, making this up. So we're given values for the magnitude and the direction of R, but because it's angled, because it's not perfectly perpendicular, what we have to do is we have to solve for our AX and our AY. We have to turn it into 1D, right? This is one-dimensional. This is perfectly vertical. This is one-dimensional. It's perfectly horizontal. So in this situation, I would turn it into a set of 1D vectors, then I can figure out my components. If I'm given a 1D vector that, well, no, that wouldn't make sense. Yeah, that's the only way. I think that answers the question. So if we're given the vector and we're asked, or if we're given the horizontal and vertical components and we're asked to solve for the resultant, if they're already perpendicular, which means they make a 90-degree angle, if they're already perpendicular, then we're good to go. We don't have to do anything. We just have to do Pythagorean's theorem and trigonometric method, and we're good. But if it's angled, what we have to do is we have to find the horizontal and vertical components. Then we can do all of our stuff to solve for the components and add them up. We're going to have to add them to whatever the other angled vectors we're working with. All right, so that is it for the 3.1 review. The quiz, remember, is on Thursday, and tomorrow we are either going to do some more practice problems, or I think we might just move on to the next section so we're not wasting too much time, because there's a lot of homework problems for you to review, and you have all of the homework corrections. I've done all of the homework problems for you. I'm going to derive any question for the quiz directly from the homework. So, yeah, we might not do any more practice problems. We might just move on. Your quiz is on Thursday. Please let me know if you have any questions. And that is it, I think. And yeah, tomorrow I'll either do practice or moving on. I haven't decided yet. Okay, let me know if you have a preference. How about that? If you have a preference, would you rather move on, or would you rather do some more practice problems for 3.1? You can leave WhatsApp me or leave a Google Classroom comment right now. Tell me what you'd prefer. If you don't, I'll just decide myself and maybe you won't like it. Okay, have a good day. Bye.